Hello everyone, I'm Mighty, your hands-on practice assistant. In this session, we'll go through a structural simulation together step by step and follow along with the practice example. Today's topic is topology optimization. When modifying a design, it is often difficult to determine which areas can be reduced and which areas must be retained. Topology optimization in NFX helps identify efficient design shapes while maintaining structural performance and reducing weight. There are two primary approaches to topology optimization. They are compliance minimization and volume minimization. Compliance minimization maximizes structural stiffness within a specified amount of material. In other words, it finds a shape that minimizes deformation while maintaining stiffness. Volume minimization, which we will cover today, reduces material volume while satisfying the required performance criteria. Today's example is a bell crank volume minimization analysis. Before we begin the tutorial, let's review the analysis conditions. In this example, topology optimization will be performed using 4 maximum load cases and the actual boundary conditions applied to the bell crank. Some hole regions will be constrained, and multiple load sets will be created to consider various loading conditions. We will also define a constraint so that the maximum displacement at a specific location remains below 0.05 millimeters. The objective of this tutorial is to find the smallest possible volume while keeping structural deformation within the allowable limit. In summary, we will obtain a volume minimization result by considering the actual loads, boundary conditions, and displacement constraints simultaneously. Now, let's begin the tutorial. First, click the New button in the upper left corner to open a new project. Then verify the unit system and click OK. Now, let's import the model. Click Import in the Geometry tab, select the example model, and click Open. Once the model is loaded, right-click in the workspace and select Hide All Guides. Next, let's define the material and property settings. Right-click Materials and create an isotropic material. Select the library material as shown. Material properties such as Young's modulus, Poisson's ratio, and density will be assigned automatically. Move to the Properties tab, create a 3D property and assign the material. Next, let's generate the mesh. Click 3D in the Mesh tab to open the Mesh Generation tool. Select the model geometry and enter the desired element size. Next, expand the More Options menu and disable the High Order Element option. In topology optimization, first-order elements are commonly used to reduce analysis time. Click OK to generate the mesh. Next, let's create a rigid element for load transfer. A rigid element helps distribute loads more effectively and provides stable load transfer. In the Mesh tab, click Element Creation to open the feature. Move to the Other category and change the selection type to Face. Select the face and use the Adjacent Faces within Feature Angle option. The selected face nodes will be assigned as dependent nodes, and a master node will be created at the center location. This approach distributes loads across multiple nodes and provides a more realistic representation of the connection. Now, let's define the boundary conditions. Click Constraint in the Structural Static Analysis tab to open the feature. Move to the Other tab and change the target geometry type to Face. Select the whole region and apply a constraint in the Y direction. In the lower right corner, constrain all degrees of freedom except RZ. This creates a boundary condition that closely represents the actual support condition. This condition simplifies the behavior of a structure connected to a rotating shaft. Next, we will define the 4 maximum load cases applied to the structure. Select the node at the top and enter the concentrated loads in the X direction and Y direction as shown on the screen. Enter the load set name as load set 1. Click Apply, then define the load at the lower location as shown on the screen. Enter the load set name as load set 1. Loads with the same load set name will be grouped into the same load set. Following the example on the screen, create the second, third, and fourth load sets. Please verify that all 4 load cases have been created correctly. Next, let's create a sensor for the displacement constraint. Click Sensor Definition in the Structural Dynamic Analysis tab. Configure the sensor options as shown on the screen to monitor the maximum displacement. Now, let's configure the analysis settings. In the Analysis tab, open the Optimization menu and select Topology Optimization. Enter a name and select Volume Minimization as the optimization type. Click Create in the lower right corner and add 3 subcases to create a total of 4 analysis cases. Click the arrow button to assign all previously defined boundary conditions and load conditions. Assign a different load case to each subcase so that all 4 subcases use different loading conditions. Next, let's define the constraint conditions in Analysis Case Control. Select Displacement as the constraint type and choose the rigid sensor created earlier. Select less than or equal to and enter 0.05 millimeters as the limit value. This optimization searches for the smallest possible volume while keeping the maximum displacement below 0.05 millimeters. Apply the same constraint condition to all analysis cases. Now that the analysis setup is complete, let's run the analysis. The analysis is complete. Let's review the results. First, let's review the material density distribution from the final optimization iteration. Regions with high density indicate structurally important areas, while regions with low density indicate material that can be removed. In other words, only the primary load paths remain in the optimized structure. Because multiple loading directions were considered simultaneously, the result reflects a design that satisfies various loading conditions rather than a single load path. Next, let's generate the optimized model. In the Optimized Model Generation menu, select Topology Optimization. Enter the target material density value and click Calculate to review the resulting volume. Set the element size to 6 millimeters and click OK to generate the optimized shape. Click Export as STL in the lower left corner to save the optimized shape as an STL file for further CAD work. This allows the optimization result to be used directly in the design process. In this result, material is retained along the primary load paths, while less critical regions are removed. Topology Optimization automatically identifies the most efficient load-carrying structure. How was today's lecture? Simulation may seem difficult at first, but if you follow the steps and practice hands-on, you can get started with confidence. With MIDAS NFX, learn the fundamentals one step at a time and challenge yourself with a variety of simulation examples. Then, see you again in the next video. This has been Mighty, your hands-on practice assistant.